second here. Okay. So I'll try sharing, although it's not, I'm not up next, but I'll try sharing.
Yeah, go ahead. Yeah.
All right, so welcome everybody to the second installment of our session, Mathematical Problems in Relativistic Physics, Classical and Quantum. Today we have a few more talks than would normally fit into the given time frame, but we will start with several 20 minutes presentations that includes 5 minutes of discussion and turnover time. And the first speaker today is Professor Donald Salisbury. And would you please share your screen?
All right, let me try this once again.
Okay.
Let's see, and I'm going to full screen. Oh, I tried. Does that work okay? Full screen?
I don't see
the full screen doesn't work for you. Just go back to the norm.
I go back to it. Okay, good. Okay. Okay. So this, can you see this screen?
Yes.
Yeah, you can see it. So that's okay. So, okay. All right. So the first presentation by Donald Salisbury, you can read its new approaches to constraint dynamics and Hamilton-Jacobi procedures in general relativity. Please, Donald. Great.
So I want to tell you about some new procedures that I and my collaborators, Kurt Zundermeyer and Jürgen Ren, have been developing. This is actually a follow-up to historical work that I've done on the earlier period dealing with Hamilton-Jacobi techniques and observables in general relativity. There actually is a recent article I deposited online. Also, there's an earlier paper that we published in 2016 that presents some of this work, and we have current work in preparation. Let's see. Also, if any questions were to arise, I'd be happy to respond. I think I may not even require my full 15 minutes to go through this. So here's a brief overview. I'm going to talk about a really earlier approach to Lagrangian dynamics in particular, but a formulation that we attribute to Élie Cartan, invariant integral. And I'm going to show you how we can extend this invariant integral approach not only to field theory, but also to gauge theories. Then related idea, I'm going to show you how one can accomplish a new derivation of a generator of diffeomorphisms in the context of general relativity. I want to tell you a little bit about intrinsic coordinates and diffeomorphism invariance, and then what implications this I think will have for an eventual quantum theory of gravity. So let me start with this Cartan invariant integral idea. Cartan proposed an alternative derivation of laws of mechanics in which he imagined that one had a closed integral over what would be solutions of equations of motions for variables q super I, but this invariant integral would be over a parameterized set of such solutions. That is all at a fixed time. And this is in the invariant integral I'm speaking of here. Whoops, I'm sorry, I was going to, I was going to time this, but I failed to do so. So this is Cartan's original expression for the invariant integral. And you'll notice that in this expression, the velocities are taken to be independent variables, because as I said, this is actually an integral at a fixed time. And it's an integral over a closed range of what will be solutions of these equations of motion. Actually, this expression, its invariance actually follows directly from the usual varied Lagrangian. But what Cartan was doing was a sort of reverse procedure in which one imposes this invariance requirement, and then from it can derive equations of motion. And I want to show you that one can indeed not only derive equations of motion, but also when one has constraints, one can also derive them. So this is a new approach to constrained Hamiltonian dynamics. I'm taking as an example here the free relativistic particle. So these are the square of the velocities. N is, you might recognize as a lapse function. So the parallel with general relativity is really quite good here. And what we're doing here is undertaking a variation of this integral and requiring that that the integral remain invariant under independent variations of all of the variables. So in particular, we're going to vary this lapse. We're going to vary what will turn out to be the velocity, and also we're going to vary the time. And it turns out then that that when one sets the coefficients of each of these variations, delta n, delta v, and so on, equal to 0, one actually derives not only the equations of motion, but also the constraints in this model. So that a variation of these velocities actually results in the fact that that what we call v mu actually turns out to be the time derivative of the position q mu with respect to t. T is the arbitrary parameter that one uses in this formalism. And similarly, one discovers that variations in n determines that this n is actually related to the minus q dot squared, the square root. Right? Then it turns out that the variation in t is redundant. It simply repeats what we found in the first two expressions. And then finally, a variation of q itself yields the sought after equations of motion. So I claim that this is actually an extension of Cartan's procedure, because it actually is now being applied to a reparameterization covariant model. And it's perhaps even more instructive to see what happens if we do this in phase space. So in phase space, of course, that original Lagrangian didn't depend on the time derivative of this lapse function. So that gives us an initial primary constraint, which I'm calling pi. And then if one inserts these expressions into the original invariant integral, giving this form, and this perhaps might look a little bit more familiar because this actually is an extension of the Poincaré-Cartan form now to this model. Well, it turns out now if we perform these same variations, but now varying p, q, and n, and pi, and also t, then it turns out if we now set the coefficients of these variations equal to 0, again, I want to remind you, this is all performed at a fixed parameter time t, then one gets this miraculous result that the first and second terms result in our sought after relationships between the momentum and the time derivative of the velocity. But then a third term yields the secondary constraint in this model, which is simply the Nash-Shell constraint, p squared plus m squared is 0. And the fourth tells us that what we call the n dot is actually the derivative of this variable n with respect to t. The remaining terms are redundant. So this is an alternative derivation of constrained Hamiltonian dynamics, but all performed now at a fixed time. So an extension of Cartan's procedure. Now, I claim that, in fact, one can carry out this same procedure in general relativity. That one can start with the what we recognize as the Poincaré-Cartan form, and then require that its variation, again, all at a fixed time, vanish. And this expression is what I call HADM, is the Arnold-Dazer-Misner Hamiltonian. And somewhat amazingly, it turns out that when we perform these variations in this model, of course, we have primary constraints to begin with, but it turns out that the variations yield not only these primary constraints, but also the recognized secondary constraints. Oops, I'm sorry. I didn't, thought I had written them down explicitly, but we get the secondary constraints. And so, as I say, this procedure that I've just outlined for you is equivalent to what I call the Rosenfeld-Bergman-Dirac procedure. By the way, you may be surprised that I've included Rosenfeld in this expression. That's actually a topic for another talk, since I and Kurt Zundermeyer have done an extensive historical work on Rosenfeld's contribution in 1930, in which he actually made some important first steps in the analysis of constrained Hamiltonian dynamics for general relativity. Okay, here's a topic which is somewhat different. Okay, so I've gone 10 minutes, I think. Is that right? Good. I think I'm gonna
5 minutes plus then the discussion session. So
okay, so I want to show you something that is related, but somewhat of an independent topic, and that has to do with what I claim is a new derivation of the diffeomorphism generator in general relativity. So the idea here is that we look at this collection of presumed solutions of the equations of motion, and we parameterize them by this parameter S. But this collection of solutions that I'm putting together then corresponds to the variation in solutions that corresponds to undertaking a reparameterization. So under these reparameterizations, we have this expression for the amount by which the position of our free relativistic particle changes, and we have an expression for the amount by which this so-called lapse function changes. Now, it turns out then that one can simply put these expressions into the what we call the conserved vanishing Noether charge for this model. That Noether charge comes about because of the identity that expresses the fact that the Lagrangian of this theory transforms as a scalar density under reparameterizations. So one determines this conserved quantity. Now, this is a bit disturbing because it includes derivatives of this lapse function with respect to time. And that is not projectable under Legendre transformation to phase space. But it turns out, if we assume that we have reparameterizations whose infinitesimal form includes this explicit dependence on the lapse function, and one inserts this into that expression that I just derived, then one obtains this new expression for the generator of reparameterizations, and this is in fact fully projectable. This is actually the reasoning that led to, in part, to derivation of diffeomorphism generators that I worked out with my collaborators, Joseph Ponce and Larry Shepard in 1997. And I claim then that this same procedure works in the derivation of the generator of four-dimensional coordinate transformations, the same derivation that I just displayed to you for the free particle. And in our derivation of this expression, we used group theoretical considerations to derive it. So this is an entirely new way in which to derive this generator. Okay, finally, I want to talk a bit about intrinsic coordinates and diffeomorphism and invariance. I illustrate this for the free particle. And for the free particle, the non-vanishing contribution to this Poincare-Cartan form is actually contains this expression P naught d Q naught. And I'm undertaking now a canonical transformation, which corresponds to choosing as the parameter time for this model the intrinsic time. And I won't go through the details here, but I claim that when one carries out this transformation, then one actually has a new generator of reparameterizations, but then one can choose as the canonical evolution variable, capital T, one can choose the parameter itself. That is, one makes a gauge choice. The result, the result is that one has then a fully invariant formulation, invariant under reparameterizations for this free particle. Now, I claim one can do the same thing in general relativity. I'm not going to be able to go through the details of how this works, but one has to find a generator capital G that allows us to transform from this contribution of the Poincare-Cartan form to a new contribution where the capital X's are phase-space functions, which we're interpreting as intrinsic coordinates. This particular idea was first formulated by Arthur Komar and then taken up also by his collaborator Peter Bergman, who, by the way, was my PhD advisor. And then I've actually shown with my collaborators that one can carry through such a choice of intrinsic coordinates in the context of general relativity. And in fact, using results that I and my collaborators Joseph Ponce and Kurt Zundermeyer have published, one can show explicitly, one can construct explicitly the corresponding invariants and show that they are indeed invariant under the full four diffeomorphism group of general relativity. So what's the quantum outlook? Well, I just have a brief statement here, and that is that the idea here is that one has managed to isolate equivalence classes of solutions of Einstein's equations. And one does so by having selected a characterization of equivalence classes through a choice of 2 times 2 times infinity to the third power constants of the motion. And one potential problem, although I think I view this as a promising claim of this new formulation of general relativity, is that one has to discover a way then of bringing into play in an eventual quantum theory of gravity all of the multiple choices of intrinsic space and time that one has at one's disposal in an ultimate quantum theory of gravity. Okay, I've gone through this very quickly, and I imagine I've managed to lose most of you in the course of this presentation, but hopefully it has at least invoked a question or two. So if anybody has any comment or question, I'd really be happy to respond.
I think, thank you, Donald. First of all, let's,
Okay.
and so we have indeed maybe just time for one quick question and a quick answer possibly, and then Shadi can take over.
Yes, Donald, does this mean that you are looking for a Hamilton-Jacobi formalism for general relativity in this way?
Indeed, indeed. We have in fact developed such a formalism, and as I say, that's partially discussed in that 2016 article in the archive update that was just posted. But we are in the process of writing an article on this procedure that will be published shortly.
Yeah, Shadi and I will definitely take a look. Okay. So time is progressing, so let's thank Professor Salisbury again.
Thank you. And I'm sorry I have to leave the session now. I have another talk coming up shortly, but I'm sorry I'm unable to listen in.
We understand.
But hopefully
so,
it will all be recorded. So anyway, Shadi, you take over.
Yes.
Thank you.
Our next speaker is Jahanur Haq, who's going to talk about Maslow's law for weak gravitational fields. Go ahead, please.
Yeah, so can you see my screen?
Yes.
Yeah, so I will talk about Maslow's law for weak gravitational field with or without a positive cosmological constant. And this is based on two works done in collaboration with Professor Peter Kruschel, Thomas Molka, and Maciej Maliborski. So let's start with the notion of gravitational wave for asymptotically flat space-time. So there is a well-defined notion of gravitational wave for nonlinear theory of relativity for asymptotically flat space-time. This is due to the work by Bondi and his collaborator. So they provided a detailed analysis of gravitational waves in full nonlinear theory, along with a definition of energy carried away from the isolated system. And the Bondi energy is defined on the cuts of Sky plus. So it is a sphere integral on Sky plus. So if you want to compute what is the, so if you consider a radiating gravitational source, just this blue wiggly line. And if you want to ask what is the Bondi energy of this space-time at this determinate instant of time, so it represents a S2 integral here. And you can show that for asymptotically flat space-time, Bondi energy is monotonically decreasing. So if you compute the charge here and the charge here, and if you take the difference, that is the difference is registered as flux across the Sky plus. And this leads to Bondi's famous Maslow's formula, which states that the rate of change of energy by a gravitating system, it related to the square of the New's tensor square of the New's tensor integrated over a sphere at infinity. So the main purpose of this talk to understand this Maslow's formula for a positive cosmological constant. So let's proceed. So given that cosmological observations suggest that our universe is undergoing accelerated expansion and which can be simply modeled by a positive cosmological constant, it is useful to ask how to generalize Bondi's formalism and what is the Maslow's formula for lambda greater than 0, and is there any analog for New's tensor, just I previously showed. And surprisingly, this remains unsolved for almost 60 years. And I must say there are some recent works to generalize Bondi's work by these two group of people. And still now we don't have any analog for New's tensor. And the lot of non-triviality comes because of the global structure of space-time. So if you turn on the cosmological constant, however small it is, so if lambda is 0, the Sky plus becomes space-like, and for lambda less than 0, it is time-like. And for lambda equals to 0, it is usual null-like. And here is the outline of my talk. So we in this talk, we ask a simpler version of the problem. We don't ask the full nonlinear theory. So we asked how to do linearized field in de Sitter background, and we wish to generalize Mondi's mass loss formula for linearized gravitational field with a positive cosmological constant. And we will work in covariant phase space formalism. So covariant phase space formalism is to compute conserved charges, conserved energy, and flux law. And as we proceed, we will discuss how to take the lambda goes to 0 limit, and we will see immediately to derive mass loss formula. The key ingredients is asymptotic follow-up condition of the field, and we compute asymptotic follow-up condition for the field in Bondi frame. Okay, and here is the metric in usual Bondi coordinates. So Bondi coordinates are adapted to the null hypercone. So this is the direction of del R along the null ray, and this is the direction of del U, and the angular coordinate are transverse to del R and del U, and this capital A represents the usual angular coordinate theta and phi, and we set our radial coordinate such that determinant of this angular metric is sine square theta. And we wish to explore linearized Einstein equation with the Bondi metric. So we take there is no source anywhere in the space-time such that TAB is 0, and we define EAB as usual Einstein tensor RAB minus half RGAB plus a cosmological constant term. And you can see from this metric there is no GRR and GRA component, which translate into the linearized case that delta GRA and delta GRR is 0, and this determinant condition translate into this condition that trace of angular part of the perturbation is 0. Okay. And we would like to derive the follow-up condition for linearized field on de Sitter background. So in de Sitter background, Bondi coordinates, the de Sitter background takes this form. So for background, actually beta is 0, UA is 0, and gamma AB is usual unit sphere metric, and V has this combination. And if you plug Bondi's answers to Einstein equation, you will immediately see there are 4 independent hypersurface equations, namely EUA equals to 0. A runs from all space-time indices. So we are working 4 dimensions. So there are 4 independent equations. And in Bondi's answers, these 4 independent equations looks like this. So details of these equations are irrelevant. What is important to realize that Einstein equation in Bondi metric forms a hierarchical partial differential equation system. So if you look at this beta equation, the right hand side is function of only gamma, and if you look at the UA equation, it is right hand side is function of beta and gamma. So given a gamma, I can extract the follow-up condition for beta, and given a gamma and beta, from this equation I can extract the follow-up condition for UV. And similarly, if you look at this EU equation, this left hand side is equation for V, and right hand side is function of gamma, beta, and UA. So given UA, beta, and gamma, I can extract the follow-up condition for V. So we linearize all this Einstein equation, and we extract the follow-up condition for the linearized field, and given a initial data. So this is the statement. So given a free data HAB, which is the linearized perturbation, and the hypersurface equation EUA fix the asymptotic follow-up condition for the field. So to start with, in HAB, there can be a term like HAB check 0 and HAB check -2 term. So if this term is there, HAB check -2, then this HUA has a logarithmic expansion. So if you don't want this logarithmic term and don't want the polyhomogeneity on psi, then you can neglect this term. So we neglect this term as we don't want logarithmic term in our expansion. And also you can see, so this term is 0 for lambda equals to 0 case, but for non-zero lambda case, you can't put HAB check 0 and HUA check 0 to be 0 simultaneously. So for lambda equals to 0 case, you can put this term HUA check 0 and HAB check 0 to be 0 simultaneously. So this is the exact consequence of Einstein equation itself. So if you look at the evolution equation for HAB, so you will get this equation. So if you want the dynamics in your equation, namely HAB check -1 to be non-zero, then you can't set HAB check 0 and HUH check 0 to be 0 simultaneously. But you can see this equation is trivial for lambda equals to 0 case. For lambda equals to 0 case, this term is not there. So you can put HAB check 0 and HUH check 0 to be 0 simultaneously by a residual gauge transformation. So the upshot is that for non-zero cosmological constant, you can't put HAB check 0 and HUH check 0 to be 0 simultaneously by a residual gauge transformation. And it has an implication to the asymptotic symmetry group of de Sitter also. So it says that the asymptotic symmetry group of de Sitter is not BMS. So in our purpose of the talk, we'll set HAB check 0 to be 0, but we will take HUA 0 check 0 to be non-zero. So this expansion is qualitatively different from flat case in this term. Now, given the follow-up condition for in bondimetric, we want to ask what is the energy associated with this linearized field. So to define the energy, we'll work in coherent phase space language. So we define a Hamiltonian for the linearized theory associated with a hypersurface sigma and a vector field x like this. So this H tilde mu is nothing but the linearized version of the Noether current. So as we are working in the linearized theory, so you take the quadratic Lagrangian, which gives you the linearized equation of motion, and you compute what is the Noether current associated with that. So this H tilde mu is nothing but the linearized version of the Noether current. So given a Noether current, then you integrate it over a three-dimensional hypersurface, and you will. So we define our energy as this integral. So integral of this Noether current to a three-dimensional hypersurface, and you can also prove that this linearized Noether current is related to the pre-symplectic current of your theory with a boundary term. And this phi tilde is the linearized field, and pi tilde mu is the associated canonical and conjugate momentum. So you can see if you take sigma as a boundary-less surface, such that if you can choose a Cauchy surface which extend all the way up to spatial infinity, then this boundary term is irrelevant. But for our purpose of this talk, we take the volume sigma as a null hypercone which intersects the sky plus to a S2. So for our purpose, this boundary term is very much relevant. And when x is the time transfer symmetry of the background, the total numerical value of this integration is identified with the total energy of the field contained in the volume element sigma. And now consider a family of hypersurface which are labeled by tau, and also the vector field, the parameter, the flow of the vector field x is parameterized by tau. Then you will ask how the Hamiltonian changes along the flow of the vector field. So if you just take the derivative of this Hamiltonian I previously defined, and using the conservation of pre-symplectic current, you can immediately show that this can be written as a boundary term only. And you can see immediately the importance of this boundary term, because some term actually cancelled out with this volume term. And you can write the flux formula as a boundary integral. So this integrand represents the flux of energy through the boundary del sigma when the volume element sigma is dragged along the flow of x. So this is a cartoon diagram for flat case, what I have just said previously. So you define your energy on this null hypercone, and your background symmetry vector is in this direction del u. So you drag your light cone along this del u, and you will receive a flux across H2 on sky plus. Okay. Now we employ our definition of this energy for the linearized field we previously obtained in de Sitter case in Bondi frame. So if you apply that, you will get this. So this is the energy of the space-time contained in a null hypercone of radius r, radius capital R. And if you look at this boundary term and you compute this boundary term with the answer we previously obtained in Bondi frame, you will see there's a divergent term which depends on lambda, and this term is usual flat space term for lambda equals to 0. And as I said previously, for lambda equals to 0 case, HUA check 0 term to be 0. So this is only the flat space result. This is correction due to cosmological constant, and this term is divergent and it depends on cosmological constant. So as our energy integral is divergent, so we propose to introduce a renormalized canonical energy, just throwing this term, and which has its own flux formula. So this term is a usual flat space term. This is like mod nu square, and this term carries the signature of positive cosmological constant. So for lambda equals to 0 case, this term is 0. So we will get back our usual flat space result. And for lambda equals to 0 case, we obtain the Bond's mass loss formula. And this is what I have explained throughout my talk. So given the fall of linearized field in Bondi frame, we compute the energy on this null hypercone, and we drag this null hypercone along the background symmetry vector del del u, and we receive flux as a S2 integral over sky plus. So this is for lambda equals to 0 case. For lambda greater than 0, our sky plus is space-like. Similarly here, you just compute the energy of the gravitational field on this null hypercone, and you drag it over the background symmetry del del u, and you will receive a flux across S2 over here. So here is the summary and the open question which we can pursue. So we provide a definition of candidate energy and energy flux for linearized field, and I have shown that asymptotic follow-up condition for the linearized field is qualitatively different from lambda equals to 0 case, and our proposed renormalized energy has a good limit for lambda equals to 0 and become classical Bondi quantities. And our works can be extended in several directions. One can ask how to add matter field, one can do the Einstein-Maxwell theory in presence of positive cosmological constant, and how can we generalize this for FLRW case, and what is the implication of this new term in the quadrupole formula, or how can it be implemented in gravitational observation. And one can also ask how our solutions, linearized solutions, are related to the linearized solution on DS background previously. So there are a lot of development of linearized solution in digital background due to the series of work by Professor Hoyts and some of my PhD work also. So how one can relate these two things. So that's all from me. So I can, I'll be happy to take questions or any comments.
Thank you very much. Let's thank Jahanur for the presentation. Time for a quick question or comment.
So I was wondering if there's some something to say about this divergent term. I mean, is there some physical underpinning there?
Yeah, so some of the comment is that you can get rid of, maybe you can get rid of this divergent term if you regularize your action by adding a counter term. I think that is one answer, but it may be due to the, yeah, go ahead.
Sorry for interjecting. But that's also like removing it.
Yes, but also if you work with Walden-Jopas symplectic current and you compute the energy flux, I think this divergent term is not there. I think that is done by this Professor Lewansky and one of the speaker in this session, Maciek Polanowski. And I think this is due to the choice of symplectic structure itself.
Okay, thank you. There is another question. Indra Neil, go ahead.
Yeah, hi. So generally, when you have a gravitational wave flux cutting two cuts of the sky plus of nil infinity, you have a memory effect associated with it, right? So in your work,
not all the time, right? So the memory effect. So if the signal has some, I mean, if the signal has different at plus infinity, at minus infinity, then there should be a memory term.
No, but generally along in the, I mean, in the sky plus only, if you have a gravitational wave flowing between U1 and U2, you have a memory term, right, which relates the two cuts. That is the super translation that relates the two cuts.
Yes, that is true, but I think again that
so
is
actually I thought in your mass loss formula you had integrated over S2. That's why you don't have this Bondi shear term, right?
yeah. So usually the mass is related to the integrated over S2. So usually there is a divergent terms in the mass loss formula, but when you integrate it, then it becomes a one-dimensional. Then you can just throw it. So usually when you derive your flux law for asymptotically flat space also.
So because we are running out of time, perhaps we can continue this discussion offline. Let's thank our speaker once again. And it's off to Michael.
Thank you, Shadi. So David, can you upload or share your screen? Okay. Not yet there. We seem to have a problem. There we go.
Okay.
Can you make it full screen?
Yes, you can see now the presentation, right?
We can, now it's, there it is. Yes. Okay, very good.
Thank you.
Okay, let me introduce you briefly. So the next speaker is David Garcia Pelaez Cruz, and he's going to talk to us about wave propagation in the ADS optical metric. Please, David.
Thank you very much, Michael. Well, this is a co-work with Cesar Simon Lopez Monsalvo in Mexico City. So I'm going, in this work, I'm going to talk about the geometric equivalence between the Fermat's and the Huygens principle in contact geometry background. These two are the most important principles in terms of light propagation. So we are going to show that the kinematics of light propagation in non-dispersive medium can be expressed by means of a one-parameter family of contact transformations. So first, I'm going to introduce some of these principles. First of all, I'm going to talk about Fermat's principle that we all know, but we have, or we think sometimes a misconception that every time light travels in an optical medium, the trajectories of the light rays are given by null geodesics. But this is not always true. Not always are null geodesics. This is a kind of simplification of a very more complex theorem in terms of variational principles in the context of general relativity. So the important thing here is that when you are talking about non-dispersive medium or media, then it corresponds the trajectory to the null geodesics that we are used to think. The other thing I'm going to talk about is Huygens principle, that in general Newtonian idea, it's a very simple principle about light evolution by wavefronts, when a wavefront is an hypersurface where different points of the wavefront can be new sources of secondary wavefronts, and they can interfere with each other and create interference patterns, as we all know. It has its counterpart in general relativity, but I'm not going to go deep inside there. But for purpose of our work, we are only going to think about wavefront as an hypersurface of all the points connected to a central point by a geodesic curve at a time t. So we can think that an hypersurface of constant time is a wavefront for geodesics. So I'm going to talk about a little more mathematical structure to work with. From now on in this work, we are going to describe an optical medium with a Riemannian manifold, B, with a Riemannian metric, G, immersed in a bimetric background, Lorentzian manifold. This Lorentzian manifold has two metrics. We first have G0. This metric is normalized to -1, the usual Lorentzian metric. But we have G tilde, which is the optical metric defined by Gordon. So this metric takes into account the real speed of light in the medium. It is this term N is the refractive index in the medium. So this complete term is the effective speed light in the medium. So the material manifold will be this quotient manifold, and we can observe that we can write G tilde, which is the optical metric, in terms of the metric of the optical medium. So we can see that the metric of the medium is just the special part of the optical metric. So we're going to work with this special part of the optical metric. So we are going to work with two different spaces that are related. First, I'm going to talk about the unitary tangent bundle. This is the common and the usual tangent bundle, but it is normalized to 1. So we can define in this space, this mathematical space, some vector fields, very important vector fields. The first one is the Liouville vector field, that it's defined like the vector field which preserves the symplectic 2 form of the tangent bundle in terms of the Lie derivative. And with this vector field, the Liouville vector field, we can define with the symplectic 2 form, we can define Liouville's 1 form. So that's the unitary tangent space. And now I'm going to talk about the space of contact elements. This is the space of elements of the punctured cotangent bundle. The punctured cotangent bundle is the usual cotangent bundle, but without the 0 level. So here again, we can observe that these elements are normalized to 1. And here with the inclusion map, the pullback of the inclusion map, we can define contact 1 form associated to the Liouville's 1 form of the unitary tangent bundle. So we can construct a contact structure D in terms of the kernel of the contact 1 form. So the manifold N, the space of contact elements with the contact structure, they are a contact manifold. And in this contact manifold, we can define a very important vector field. It's called the Rev vector field. And this Rev vector field is defined in terms of the evaluation of the contact 1 form. So this vector field evaluated in the contact 1 form is 1. And in the exterior derivative of the contact 1 form is 0. So it is like a transverse direction of the contact distribution of the hyperplanes. So this distribution is very important because it's the one that is going to make a relation between the space of contact elements and the unitary tangent bundle, by demanding that the Rev vector field in the space of contact elements is proportional to the velocity of the geodesics in the unitary tangent bundle. So here we have this kind of transversality notion. So this duality between the Rev flow and the geodesic flow, it is only true, this is for a simply connected non-dissipative medium. The contact elements are transversal to the speed of the geodesics, of a geodesic curve. So we can observe that here in the figure, the contact elements in light blue are perpendicular to the vectors of the geodesic speed in the geodesics V. So there exists a family of a one parameter family of contact transformations to the space of contact elements to itself that transform the points. And if you start with a point in a particular geodesic, when you transform by this family of contact transformations with this parameter T, then you stay in the same geodesic. It doesn't change the geodesic which you are moving. So you can observe here that you can think that the evolution of the geodesic flow is given by the one parameter family of contact transformations. So this is a very important relation, because if we want to solve or to construct light rays and wavefronts in optical media using this tool, it is much easier to solve Reeves flow to solve the geodesic equation. So we can find all the wave propagation in terms of wavefronts and light rays only solving the Reeves flow instead of solving the geodesic equation. For not simply connected spaces, for example, if you have boundaries or you have discontinuities, or maybe you have interfaces, the transversality of the wavefront and the geodesic is not completely fulfilled, but this formalism is broad enough to work with these interfaces and stuff like that, and we are going to see some results. So with this tool, we construct some known light rays and wavefronts in the Minkowski optical metric, the flat one. So here we made a little test. In the right part, we can see that we put a light source in a medium, in this case air, and then we construct a thin layer of another medium, in this case was water. So we can observe that light rays refract, and we can reconstruct Snell's law of refraction with this reconstruction of the Reeves flow. And we can observe again that the wavefronts here, we can see that they deform when they pass through the interface of water, and the delayness of the wavefront when they come out of the interface. And in the left part, we put the light source in the different media, which is in this case water. So we can observe that there are some light rays that do not come out from the water. This is a very well-known phenomenon called the total inner reflection. So there are some, for some angles, here we have that the light rays do not come out from the water. We are not representing those rays here. We are only representing the light rays which come out from the water. We can observe again that we have the deformation of the wavefronts, and here far away from the light source, we can observe some this phenomenon of not perpendicularity between the wavefronts and the light rays, and this can be explained with some phenomenon of aberration, optical aberration, and stuff like that. So now we use this information to make the optical metric of the anti-de Sitter model space-time. So here we have the geometry of the anti-de Sitter mapped to a Poincare disk. So here again, we are constructing two interfaces, a vertical one, the left one, and an horizontal one, the right one. So we can observe in this geometry, again, light rays are refracting when passing through the different media. So we can observe the wavefronts that evolves and how they deform when passing through the interfaces. So this is the most important figure and result with this tool. We put the light source in the different media, in this case in the water, and we observe first of all that no total linear reflection is seen in this anti-de geometry. So we can observe two different very important phenomena that are to get discussion. Here we can observe in this part that the ray lines that come out from the outer part of the water interface are not transversal, not at all to the wavefront, not even, they are not transversal, so we can observe that even this part is sorry for this. We can observe that these wavefronts here again, okay. So here we can observe that the light rays are even tangent to some wavefronts. So these transversality not fulfilled could be acoustic, as it is defined by Perlich in its book. So these caustics can be made when the transversality between the wavefronts and the light rays are not fulfilled. But here we are not observing intersection of light rays, which is another condition to have caustics. But it could be explained something like that. And other part, interesting part, is that we can observe that some light rays, when they come out from the water, they intersect more than one time the same wavefront. And if we think that the wavefronts are hypersurfaces of constant time, then it could be an interesting phenomenon here that light ray cross more than one time. We are thinking of interpretations of this. We can think about the anti-de Sitter model, which is not completely hyperbolic. So we can have achronic surfaces. So maybe this is part of these achronic surfaces here in this part. So this is our results, and as a closing remarks, well, the contacted geometry works as a unifying framework for light propagation theory. We have two important mathematical structures: the unitary tangent bundle, where Fermat's principle live, and where light rays can be evolved as flows of the Reb vector field. And we also have the space of contact elements, which again in Perlich is defined as the optical ray structure geometrically, where we can construct wavefront tangent to contact elements, and the evolution here is associated to contact transformations. So the important thing is that the entire nature of light propagation in non-dispersive media is encoded in the contact bundle of the optical manifold B with the metric G, together with its symmetry. And this is we think it is a very important tool, because it allows us to construct light rays and wavefronts without solving either directly the geodesic equation nor the wave equation. And it is a very economical way to deal with interfaces. And I think it's a very, very, very good technique that can help and can be used in some other in some other context of general relativity, for example, some interfaces with vacuum and plasma and stuff like that. So that would be, for me, the presentation. Thank you very much.
Okay, so let's thank David Garcia for this presentation. So maybe we have time for one quick question again. We are running out of time.
Yes, I have confessed I'm a bit troubled by speaking of water in anti-de Sitter space-time. I don't understand what that means.
Well, what we are thinking is to use, is to reconstruct like interfaces and refraction in the anti-de Sitter geometry model. So we take the anti-de Sitter geometry, like from the space-time, and then we made the exercise of thinking of refraction, on how the light rays will be refracted when passing through different media. But we wrote water because we use the refractive index of the water and the air. So we can make this kind of exercise to see how wavefronts deform and to see how light rays refract. That was the exercise of the anti-de Sitter. The important thing here is that this model is broad enough to work in different geometries and to work with different properties of space-time that maybe we can use it later to more applications.
Okay, thank you. We have to go on. Let's thank David again.
Thank you very much.
And Shadi takes over.
Yes, Maciej, could you please share?
Yeah, let me share it. This one, I think. Okay, can you see my screen?
Yes, it's a pleasure to hear Maciej Kolanovsky talk about wall-Zupas charges in asymptotically de Sitter spacetimes. Go ahead, please.
Thank you. Let me start by thanking the organizers for the opportunity to speak at this nice conference. So I will say about some particular construction of charges in the gravitational theories in the case of positive cosmological constant. To put it into a little bit more context of today's session, one conclusion from this talk is that this renormalization of gravitational energy that we heard 2 talks ago is actually unique. That it seems to give a correct answer and that there is no ambiguity in this regarding adding some further counter terms. So why should we even care about asymptotically de Sitter spacetimes? Well, the basic thing is that according to almost all observations, our spacetime is filled with positive cosmological constant, either in dynamical sense or just a constant, but one shouldn't ignore it. And unfortunately, the whole description of gravitational waves so far, starting with Trautmann and Bondi and Sachs and Penrose, it all happened in asymptotically flat spacetimes. And despite the fact that cosmological constant is extremely small, that we don't expect it to change anything, it leads to really huge differences in the framework or in some conceptual issues. That's because our infinity, our sky is actually space-like, as we again heard today. So whatever our energy would be, it cannot be positive definite. Moreover, there is no universal structure on I+, or to be more precise, the only universal structure is a structure of a smooth
manifolds. So our asymptotic symmetries, which preserve these universal structures, are all diffeomorphisms of null infinity. So there are no distinguished generators that one could use. So there are huge conceptual differences, and natural question is, can we actually measure the fact that we need something totally different, or is it just a mathematical curiosity? Let us check. So I will start by explaining, or rather reminding you, what is Wald-Zupa's approach to defining charges in gravitational theories. Then I will apply it to, then I will say a few more things about asymptotically de Sitter spacetimes in general, about the initial value formulation, and then I will apply this Wald-Zupa's approach to those asymptotically de Sitter spacetimes and prove and show that there is uniqueness of charges under some very natural conditions. And this also, as I said, this will also gives this uniqueness of this renormalization procedure that Yahanur used in his talk. Then we'll go through some examples, and this will be it. So what's the general idea? We have some hypersurfaces in our spacetime that are going up to infinity. Here it is a figure for lambda equal to 0. So null infinity is, well, null. So we have those hypersurfaces, and we would like to associate a charge with each of those hypersurfaces in such a way that the flux that we would have some flux of these charges, and so we could measure, for example, how much energy was in one slice and how much energy is at the end. So in other words, how much energy was radiated away. And we will want to do exactly the same in asymptotically de Sitter spacetime case. The only difference is that I plus is now space-like hypersurface, so that's the only reason in this picture. But we want exactly the same thing. So in symplectic geometry, the way to define charges or Hamiltonians is by the following. Let me write on it, formula. If your theory is diffeomorphic invariant, you can write it down as some boundary term, but there is problem. The problem is that usually this is not going to be the true variation. So this is why this variation here is crossed, because when we take the second variation, the second variation, we obtain some terms which in general are not vanishing unless omega is very special on this boundary of our hypersurface. And in this case, this boundary is just a cross section of this hypersurface with I plus. So the idea is that we should change this by adding some additional term to make it a true variation. Okay. So one can check easily that what we need to add is something of a presymplectic potential. It's not exactly presymplectic potential because it's going to be defined only on our I plus, and its variation is going to give a pullback of presymplectic current into this I plus. So a priori, it can be different than true presymplectic potential. And then one can check that the flux is actually given simply by this presymplectic by this theta term. Anyway, and of course, in this construction, we have an ambiguity that we can add something delta exact to this theta, and then we change our flux, but well, we have well-defined Hamiltonian anyway. So the idea of Wald and Zupas was to assume that this theta is a local object, which depends only upon dynamical fields and universal background structure. Here we don't have any universal background structure, that it should vanish whenever it is evaluated at a stationary solution, which makes sense since it is supposed to be flux, because we don't want to have any flux for when we have a stationary solution. It should depend analytically upon in our dynamical fields. It doesn't mean at all that we are in analytic category of solutions. Solutions can be whatever class they should be, but our Lagrangian is usually analytic in our dynamical fields. And moreover, it shouldn't depend upon any arbitrary choices like conformal factor. Okay, so that's about world Zupas for now. Oh, and it was proved by those two people that there is actually unique theta like this. And in this way, they derived fluxes for BMS. Okay. And now about asymptotically de Sitter spacetimes, we will describe them using Pfefferman-Graham gauge. It can be shown that this spatial metric has some expansion in this road parameter, and our scry corresponds to rho equals 0. And now G1 and G2 are completely determined by G0, so by this leading order. And G3 is pretty prescribed up to the following constraints: that it's supposed to be traceless with respect to this G0, and divergentless again with respect to G0. For convenience, we will use rescaled G3. This is so-called holographic energy momentum tensor. It can be shown that those G0 and T are defined up to conformal transformations. In Pfefferman-Graham gauge, those simply means different choices of slices of rho equal constant slices. And it can be shown that actually a conformal class of those two tensors at scry, which satisfies those constraints I just mentioned, uniquely defines solution, at least if those G0 and T are close enough to de Sitter, the space of initial data. In the Pfefferman-Graham gauge, it simply means that Gn all satisfy recurrence equations, which can be unambiguously solved in terms of those initial data. And from this, we can we have our solution. So then one can calculate limit of the symplectic current when we go to rho equals 0. And in fact, this limit is equal to the symplectic current in the bulk. So we are not losing any degrees of freedom in contrast to the asymptotically flat spacetimes. And it should be obvious from the previous slide, since this I plus here is Cauchy surface. Actually, to get this omega, you need to add some counter terms. Omega obtained simply from Einstein-Hilbert action is divergent. And one can immediately see what our theta should be, right? We can just remove one of those deltas and we have it. Okay, so according to, we add this term to this, according to this general prescription, it can be checked that this, that now Hamiltonians truly exist, and they are given by this holographic energy momentum tensor. Okay, but what about uniqueness, right? Because I told you that I can modify this theta by adding to it a variation of whatever I want, and it is equivalent to changing counter terms added to my Lagrangians. So can I have some additional? Can I add some counter terms? Here is this wish list of Wald and Zupas, and we can see that we cannot actually impose all of those because I plus is space-like, so it doesn't make any sense to say that something is stationary there, right? So we need to get rid of this condition. And actually, then we discovered that with those three, there is a unique choice. And this is exactly the choice okay, this choice is the unique choice that satisfies those three conditions. So there are no counter terms that could be added to your Lagrangian, and this is the reason why this procedure is unambiguous. Now we can calculate, we could linearize our solutions and check whether they agree on or not. And in fact, yes, they do agree with those results in the linearized theory as calculated by Hrushchel, Hoke, and Smoka, and also my advisor and myself. Moreover, they have correct limit as lambda goes to 0. One can similarly treat perturbations around Schwarzschild de Sitter, where we have distinguished rotation generators, so we can calculate angular momenta of our gravitational waves, and we can calculate time translation generator. We have time translation generator, so we can calculate energy. One could do the same in the case of the Kerr de Sitter, but then it's a little bit problem now because we don't have d upon d phi, so angular generator angular momentum generator is well defined by the condition that it's supposed to be a Killing vector which has closed orbits. Okay, but then we don't have any natural time translation generator because we don't have any time because we can add any to this d upon dt, we can add d phi with whatever coefficient we want. One choice that one could make is to add this d upon d phi in such a way that those two Killing vectors are orthogonal to each other at scribe. This is conformally invariant condition, so perhaps it makes sense, but it's open right now whether there is any physical reason to just choose this team, and how we should extend this choice away from the Kerr de Sitter. So we derived charges and fluxes for asymptotic de Sitter spacetimes. They're unique under highly natural conditions. Their expansions around symmetric spacetimes agree with linearized theory. They have correct lambda going to 0 limit, but we still are not sure how to define energy in the full theory. If I have one more, do I have one more minute? Or
yes, go ahead.
Okay. So I have one additional slide for. We have one idea. There is a large class of initial data for which G0 can be written globally, which is important here, in the following way. It actually follows from the Hrushchel's PhD thesis, although in a totally different context. Then one could take d upon du as time translation generator, and it makes sense in then if we have some decay, reasonable decay conditions, that this G0 is like in de Sitter at u going to minus and plus infinity, so basically it is stationary, then this coincides with this correct and this correct time translation generator. It works with it coincides with our previous simple examples, but still it's a geometrical construction, and we are still investigating whether there is any physical reason to try this one. Okay, and now that will be all. Thank you.
Okay, let's thank the speaker for this presentation. We have time for one quick question or comment. Go ahead.
Hi. So you said that there's ambiguity in a choice for capital theta, right? Which is in boundary.
Yeah.
And you make a comment that this is analogous to add a counter term. I think the ambiguity is in two.
Yeah, okay, so by counter term here, I mean boundary counter term, only defined on a scribe.
Boundary counter term, not in the Lagrangian, right?
I'm not in Lagrangian, but in the full action.
Yes, because
to obtain this finite symplectic current, you already need to add some boundary counter term, which is infinite, of course.
Yes, this I agree, but the ambiguity in capital theta is coming from the ambiguity for omega, right? And this ambiguity is completely different from adding a boundary term in the Lagrangian itself. I think if I understand correctly, Wald and Jopas has also a discussion of this.
No. The point is that you want variation of theta to give you omega, right? So if you have this omega,
so at first you compute omega, then from there you can
okay.
Right?
One thing
so
I didn't say, I understand now. One thing that I didn't say is that what we checked is actually that there are no functionals at Scri that satisfies those conditions after variation. So in this sense, you don't have counter terms.
All right.
But because what we actually checked is about functionals and not about theta. These theta things follow, but also additional, we know that there are no possible counter terms.
Okay.
Which are finite.
Okay. All right. Well, thanks again for this presentation, and back to you, Michael.
Okay, thanks again, Shadi. And our next speaker is Dr. Emine Simon Kutluk. And would you please share the screen?
Yes. So, can you hear me?
We can hear you, yes, but we don't. There's the screen. Yep.
And you see it now?
Yeah, now we can see it. Thank you very much. So let me introduce you. Okay, so as I said, next speaker, Dr. Kutluk, and she is going to speak to us about adiabatic solution of general relativity as geodesics on group of boundary symmetries. Please.
Thank you very much for the opportunity to talk. So let me start with our motivation to do this study. So there has been a rising interest in studies of asymptotic symmetries and soft theorems. And this topic was investigated in flat space, but also in cosmological perspective, somewhat independently. And in the cosmological side, the studies heavily relies on Weinberg's argument for the existence of what is called adiabatic modes on a generic cosmological background. So in this argument, he starts from some pure gauge modes, and he produces some physical low frequency modes. So we use a similar trick for general relativity in a Manton approximation. And in Manton approximation, one just sees slow time trajectories on space of static and minimum energy solutions are good approximate solutions. So we will be utilizing this. And for our case, I'm going to show you that those trajectories are to be null geodesics on the space of diffeomorphisms of the boundary of the spatial slices of our space-time. And we also formulate this in the language of geometric continuum mechanics. And I'll also show you some special cases of 3+1 and 2+1 dimensions. So let me start with describing what is Manton approximation, and because this is our basic starting point to study these adiabatic solutions for general relativity. So let me have a set of fields phi I on a space-time described by t and x coordinates, and let me have the action written like this, a kinetic and a potential term. And let me consider the configuration space, the space of static fields. So here, all of this will be my configuration space. And now I should also assume that the potential here have a continuous set of minima. What does that mean? Is that in the configuration space, let there be a submanifold E such that the potential is extremized. So these static fields will be solutions to equations of motion, because for this action I have, the equation of motion is like this. So when you have static fields, the left-hand side is 0, and when you extremize this, you solve the equation of motion. Now, I had this metric Gij on this configuration space, because these phi dots are basically tangents. So that metric will induce a metric on E, the space of extremizers of V potential. And this is Monton approximation. This tells us that a geodesic on this E with respect to this metric I showed you, Gij, that is slow in time, is a good approximate solution. And I can ignore the motion of this E. So now how do I apply this to general relativity? First, I should bring my Lagrangian into the form I showed you. It should be a kinetic plus a potential term. And this I can achieve by going into ADM action and then choosing the Gaussian normal coordinates where G00 is -1 and G0I is 0. So these are lobes and shift. Sorry, I take lobes and shift to be 0. And in that case, the action really takes the kinetic and the potential term. And here the kinetic term has this form. Okay, so whatever I put in here, as I can consider this as vectors, I just plug in here. And potential term is simply the Ricci scalar of the spatial slices. So this GH I introduce here will be the metric on the configuration space. So note that these lobes and shift are Lagrange multipliers. So from now on, I have to impose the constraints of GR externally. And they take this form under this Gaussian normal coordinate choice. So this first one is the momentum constraint, and this one is the Hamiltonian constraint. So now I brought my Lagrangian into kinetic and potential term. Now I have to identify the set of static solutions that extremize the potential. The potential is not bounded from below for GR, but it is extremized if I choose my spatial slices to have flat Rij. So these metrics, Ricci flat metrics, and their gauge transformations will be my set of static set of extrema. So for our investigation, we will just focus on one reference metric and its gauge transformations. So E is composed of basically just transformations of a single metric. So now also remember that I'm in the Gaussian normal coordinate, so I have chosen a gauge. So my remaining gauge transformations, this psi, are not full set of diffeomorphisms. They actually turn out to be these two sets. So one of them is simply the spatial transformations, and other one has this peculiar form. We call it local, so it has time and space parts. And these second type are, first, they're field-dependent transformations. So I have the metric here. So they do not form a proper algebra. And they also have a different interpretation. So because of this, we restrict ourselves to just the set generated by the spatial transformation. So my E is going to be set of H metrics that can be written as this. So I have a single reference metric, and I just gauge transform that. So Z here just parameterizes different transformations. So now, this is the point where I bring in the dynamics. Now I conjecture that, or impose that the time dependency of my metric comes in just inside this parameter of the gauge transformation. So note that this has some trickiness. So this is a gauge transformation when you consider a single spatial slice, but when I have all of slices together, and if I change the coordinate transformation for each of the slices, this will no longer be a diffeomorphism of the space-time. So I will produce a space-time that is different than, for example, if I start from the flat metric, the thing I am producing will be different than a flat space-time. So let me show this. So let me take as a reference metric the Euclidean flat three-dimensional metric. So, and let me, for transformations, let me write down this. Then, if I just do this, I will produce this space-time, which is just FRW, flat FRW. So this illustrates that this procedure really produces physically new solutions. So let me continue with my investigation. So this is the proposed solutions to Einstein equations. And if I wrote down this and take the time derivative, I will have the following extrinsic curvature. And if I plug, and here the nabla is the covariant derivative belonging to H, this H. So then I want to plug this in everywhere for the everywhere, and by that I mean in my constraint equations, which I impose externally, and also in the action. So the momentum constraint becomes this, and here I'm also using the Ricci flatness of each slice. And Hamiltonian constraint becomes this. And the metric on this vacuum space is this. So these are the things that describe my theory now. And my psi is my basic field. So as I noted, the solutions, the actual solutions will be geodesics with null geodesics, sorry, geodesics with respect to this metric. And the fact that I have this Hamiltonian constraint, which is exactly put in here. So putting Hamiltonian constraint to 0 means those geodesics have to be null. So Hamiltonian constraint restricts the geodesics to be null. So this is different than other classical applications of Monton approximation. And now I'm going to continue with my investigation, but I'm going to change my coordinate frame again for each slice, because each slice is diffeomorphic to this flat slice. So I'm going to the coordinates where my metric has this flat form, so that my equations become simpler. So I'll just push forward my psi to the reference frame where I have this flat metric. So again, so this describes my theory, and I just should move on trying to solve these constraints and try to make sense of this metric. So now I'm going to show you this metric I have, which describes the dynamics, actually is composed of boundary data. And by boundary, I mean the boundary of each spatial slices. So for this, I have to impose that my vector fields are boundary preserving, so they have zero normal at the boundary. And then if I go on with my calculations, it turns out that I have this metric. Now, this is evaluated on the boundary of M. And this K is the induced metric. Curly K is the extrinsic curvature of the boundary. And sigma A are tangent component of the sigma to the boundary. This definition of the orthogonal, it's basically a normal derivative. And let me for now ignore what these are. These are just foliation parameters. So here, everything is composed of boundary data, the sigma A, K, and the determinant of K, except this orthogonal derivative. So now I have to show that this is also composed of boundary data. So for that, I use the fact that I still need to solve this constraint equations. And what we can show is that, let me be a little bit fast. What we can show is that there is a unique sigma that satisfies the momentum constraint and the boundary conditions we impose, but it's unique up to some exact forms only. This exact form, we conjectured that it's going to be fixed by the Hamiltonian constraint, but we were not able to prove this. But however, to show that this metric is composed of the boundary data, actually one does not need this last conjecture because this unfixed part and its normal derivative is actually one can show to be composed of the boundary data. So in conclusion, this metric I have defined is solely composed of boundary data. And because of that, I can also consider it as an inner product on the space of boundary vector fields, which I wrote down as Z. So now if I believe this conjecture that I can fix all my vector fields using the constraints, then it turns out that, so I already showed, the set of space of vector is just diffeomorphisms of the boundary, but then I have to quotient out by the isometries of my metric, because this will disappear in the metric I have defined. So remember that initially my metric was in this form, so isometries have to disappear here. So to have my metric non-degenerate, I have to quotient out by the isometries. And actually, one can show that this metric I defined is invariant under this diffeomorphism. So it is also, so this B is a Riemannian homogeneous space. So this metric will have a mixed signature because it has these minuses. And actually, one can see that this because I can define this operator D here, and this can be made to be 0 for some zeta, if zeta is in the kernel of D. The isometries are necessarily in this, but we also don't know if this works in the other direction. So one other thing I would like to add is that this metric we have found is actually akin to some of the expressions in continuum mechanics. So this, without D, you have this in continuum mechanics. Well, with D actually, but it's not written in this form. But so this D we have defined, and it's fixed for general relativity. But if you keep it generic, you find that the equation of motion coming from this is this.
Excuse me, actually running very short in time now. So
yes,
can you
yes.
come to the punchline?
Yes, yes, I'll wrap up. So if you choose this D, like identity, it gives Euler equation. If you choose it like this, it gives Kamasa-Holm equation for shallow water waves. So we have studied some examples. I'll just very quickly go over it. So if I have consider a flat ball with round boundary, for example, I can show that my metric takes this form. So I have two free parameters here. One of them is ALM, and this FLM is a function of R. So one of them is related to curl part of my vector, and these FLMs are related to gradient parts of my vector. So for example, from this, first we see we have to have,
please. We are really out of time, so
okay.
let's come to the conclusion, please. I'm sorry.
Okay. Yeah, I just want to say you have to have both of the towers to set this to 0. In 2D, one can show that Hamiltonian equation becomes the real Monge-Ampere equation, and its solutions are known. In 3D, we could not find a specific solution, so this was important. So let me conclude. So I showed that using monotone approximation, we can propose some adiabatic solutions from diffeomorphisms. And with this, the space of vacua is diffeomorphisms of the boundary quotiented by the isometries. We can define a metric on this space, and our solutions will be null geodesic with respect to this. I showed you that our formulation is akin to the continuum mechanics, and I showed you some of the 2D and 3D examples. So I think I'll just stop here. Thank you.
Thank you very, very much. But since we indeed are already 1 minute in the next talk, I'll give it right over to Shadi, who will introduce the next speaker. Sorry, we don't have time for discussions. Maybe you can send things to the chat. Shadi.
Thank you. If you please stop sharing so that the next speaker can. Okay, thanks. Giuseppe, can you please share your
Sure. Okay, can you see my screen?
Yes.
Okay, so first of all, thank you so much for the opportunity of giving this talk today. Today I am about to talk to you about averaging cosmological observables in large-scale structure surveys. So I feel the need just before starting to say a few words about my research interest. In particular, I'm a theoretical physicist whose the main interest is to study what are the formal aspects connected to general relativity in order to properly understand and study nonlinear effects in the evolution of large structures nowadays. So in this regard, just to have in mind that my general framework is related to general relativity, one of the main problems which turns out to be relevant today, according to the precision that we will achieve in the next decades from the observation, is just to be comparable at the same level of precision in between of the achievable precision from the experiments and the theoretical prediction from the theoretical models that we want to test with the observation. So in this regard, the next decades will be very exciting because we will have access to a huge amount of data, which at an unprecedented level, and in particular the interest in studying nonlinear effects in the late time evolution of structures in the universe is not only in the fact that we will be able to observe them in the next years, but also in the fact that also due to the progresses that we are achieving from the computer sciences, and in particular to developing n-body codes from the relativistic viewpoints, there will be also a huge plethora of data which will allow us to test at the same time theory, observations, and numerical aspects of relativity. So in this regards, given these motivations, the main things that I want to discuss with you today is related to the fact of how should we properly average observables when we have access to a huge number of data from the observation that we can get from the universe. And in this particular regard, the main interest is to properly define from the theoretical viewpoint, from the mathematical viewpoint, what are the prescriptions allowed for comparing observations and prediction from theory, as long as we make our measurements directly on the light on the past light cones where our measurements actually lies. So this is just to give you some ideas about how complicated, I mean, how subtle is this point. I would want just to show you three particular examples about the three different kinds of observations that the observers actually aim to do in the next years. So in this figure, we see that we might have, for instance, a given source in the universe given by this big black point here, which emits, let's say, photons, which travels along this cone here. And according to, let's say, at a given shot of the universe, a given snapshot of the universe, we can observe along the same past light cone several same kind of sources emitting, for instance, all of them photons. And in particular, in this way, we know that from the mathematical viewpoint, we have to identify the proper set of equation of mathematical framework to describe the situation. This situation, however, might be very different if we have access to other possible cosmological probes. For instance, we might deal with the same kind of source, which is emitting different kind of messengers. In particular, we might have that some of the messengers that we identified from the given source is not traveling on the light cones. In this sense, then we have to deal with another possible prescription for averaging all this information that we are getting from these cosmological sources in a way that we have to properly compare different cones, eventually even not light-like, in order to properly understand and to properly constrain the models that we want to study across the universe. In this regard, then, we can identify a set of 4 questions, which will allow us to set the general framework, which will allow us to identify the given prescription once we have in mind what we are observing in the universe. And in particular, we have to answer those questions here. First of all, what is the physical object, the physical observables that we are looking at in the universe? Secondly, what is the type of messengers that we are receiving? So in particular, if we receive signals which travels on light cones or massive cones, this can play a role and can lead to some misinterpretation of data if this effect is not taken into account. And secondly, how do we foliate those? I mean, how do we locate those sources in the universe? Because we know that since we deal with 4D pseudo-Riemannian manifold, what we have to do is that we have to properly locate, properly slice this manifold in order to to be related to the actual object which we are looking at. And last but not least for importance, of course, what is our state of motions? I mean, how we are moving according to our local motion in the local galaxies or in local cluster of galaxies. Having this in mind, then the mathematical translations of those questions stands in the addressing the proper scalar fields, which precisely answer to these given questions. In particular, for all of the above mentioned questions, we can identify a scalar field, and by scalar field I mean scalar just under the diffeomorphism allowed by general relativity, which can identify, first of all, what is the observable we're looking at, what is the properties, what are the properties of the messenger that we are observing, and what are also the other properties related to the state of motions of the observer, and in particular, how do we connect observable between themselves. Given this in mind, that in particular I'm going to discuss now two peculiar examples which are in particular of interest in cosmology nowadays. And first of all, how to properly define on the light cones of these messengers two-dimensional hypersurfaces rather than three-dimensional hypersurfaces where the small where, for instance, I just choose a cut in the third dimension, which might be small enough to be considered infinitesimal. In this regard, then, the true prescription that me with my collaborators identified in this work are given by those two prescriptions. And I mean, just by looking at them, they might look a bit complicated, but you can convince yourself that the presence of these gradient projected onto this scalar field, onto the gradient of the scalar field here, and the appearance of this peculiar specular part regarding this field here, is properly the mathematical object which allows you to say that regardless of the coordinates that you are adopting to do these averages, those results are invariant under the reparameterization of those fields, and are also gauge invariants under the possible set of coordinates that we want to adopt to make our predictions. Given that, then, I mean, this prescription might look very, very interesting. I just noticed that the only difference between those two stands in this prefactor in these factors here in the integral in the two-dimensional one, but are still very formal. And the things that we want to understand is whether we can actually do some prediction, which we can actually have some control from this very formal starting point to the comparison with the observation. And in these regards, we have in mind, for the purposes of this talk, for instance, what happens to the flux of photons emitted by given sources traveling on a past light cone of sources where the distance is given in terms of the redshift that for the sources that we have access to as well. In this regards, then, the only things that which is left to be specified is the state of motion of the observer, which is taken to be geodesics and free falling, as our laboratory might be on on larger scales than the galactical ones. But still, to achieve proper comparison, what we work within is we work with this set of coordinates, which is a set of coordinates where the only thing which is specified are the gauge freedoms allowed by general relativity, and in particular, we have those coordinates here are such that W is a null coordinate which exactly reproduce the past light cone of the observers. Fully nonlinearly. So it means that whatever kind of nonlinearities or inhomogeneities light might encounter towards it's traveling towards us, everything is properly described by this line element, since no symmetries are required here. And in particular, this is very interesting, especially for cosmological applications, since we can immediately say that just by writing down this line element, we can already identify basically the ingredients that we need to apply our prescription for the averages. In particular, we have that since this line element exactly solves time-lag geodesics from comoving observers and light-lag geodesics, we can identify W as the scalar fields needed to identify the traveling of the photons, and tau with scalar fields identifying the motion of the observer. And the other two objects that we need are just the redshift, which turns out to have an explicit exact expressions in those coordinates, in these coordinates, and also the expression for the flux of the flux received from a given source, which is nothing but, let's say, a power of the so-called luminosity distance. In this regard, then we have that if you have a look about those prescriptions here, you can see that the only different part appearing is given by, as I told you before, by the presence of this prefactor here in the integral. The difference then here is given by, is explicitly given by those two terms, where now we have that we are explicitly translating, thanks by coordinate transformation, the result as obtained in the geodesic light coordinates, in geodesic light cone coordinates, into a perturbative schemes where scalar perturbation for the longitudinal gauge are chosen. In this regard, we can see that those two measures in the averages that we want to study are similar but not exactly the same. And in particular, we can identify that these terms here, which is where this v parallel is nothing but the radial motion of the source, it's the radial velocity of the source. Those terms here turns out to be the same, but there are some differences in other terms which are which can play a role in some specific range that we want to show you. I want to convince you about just in few slides. This correction then to the average for the average of the flux can be summarized just by this writing here, where we have identified those factors here according to the chosen prescription we want to do, whether it is two-dimensional or three-dimensional one average on the light cones. And in particular here, just to say that what we are doing here is that these brackets here, these brackets here refers to the fact that we are averaging all over the sky. So we are assuming that the perturbations are stochastically generated. And just by looking all across the sky surrounding us, it's just a reproduction of all the possible perturbations that we might have today. And the amplitude of those perturbations is given by this further ensemble average given by this overbar here. This is just to explain what is written here. In particular, now we can see that those two prescriptions turns out to returns results which are almost on the same level, where here we have that this black solid line is just the pure contribution which is in common between the two prescriptions, which is just to the part that they share in the measure. But we can see that once we had also the peculiarities due to the exact mathematical structures within the 2D or three-dimensional case, we see that the corrections are almost of the same level, and this is just can be addressed to the fact that we are working within perturbative theory. But there are some differences, in particular when we move to higher redshifts. So it means when we go farther beyond in times. And those differences might play a role, in particular in the fact that in the next decades, the observation that we aim to achieve about the universe precisely wants to go towards higher redshift in order to properly understand the nature of dark matter, the nature of dark energy, and also the initial condition that from where perturbation and nonlinearities as we see them today have origin. Just last thing, I think that I have a couple of minutes more, right?
You're almost out of time, so
Okay.
just please
very
wrap
good.
up.
So just the last very things I want to say is that this formalism can be extended also to the case where we want to decide to be driven by more observation-oriented averages. For instance, we want to weight by the number of sources as we observe them direction by direction, but this can be exactly generalized by substituting the S field by a proper weight given by the matter density field. And as long as this field here is as well as scalar field, the procedure explained before is perfectly legitimate and can be applied as well. And the difference when we do that is here. And again, just by looking at this other possibility, which is more observation oriented, since exactly deal with number of sources as we observe them across the possible direction in the sky, we see that differences starts to be very relevant, and in particular there is also switch signs which might alter it a lot the results when we want to compare them with observation. So the main take-home message basically is that this formalism can, of course, will be of certain importance for the next decade's observational cosmology research program, and must be taken into account in order to properly compare not only theories with observations, but also with numerical simulations, and in particular from the with the non-Gaussian effects, which are starting to be detected from the relativistic embodied simulations available in the last few years. And with that, I have concluded, and I thank you again for the opportunity.
Thank you very much. Let's thank the speaker. Unfortunately, we are pressed for time, so I invite you to direct your questions in the chat to Giuseppe, and it's back to Michael for the next speaker.
Thank you, Shadi. And I wonder, is Panibrata back?
Yeah, yeah, I am.
Okay.
Shall I share the screen?
No, we hear you, but I don't see the screen. Please share.
Yeah.
Okay, here we go. Now, if you can make it full screen, then we are all set.
Yes. Yeah, I'll do.
So meantime, I can introduce you. Okay, our next speaker, Panibrata Mukhopadhyay, and he will speak on the gravitational geometric phase.
Thank you for accommodating me in this session. I'll start running my stopwatch to make sure that I'm on time. Okay, so as it is announced, my title is Gravitational Geometric Phase. I essentially will cover the result in 2 papers in this archive and published a couple of journals sometime back. One is this year, of course, with Tanuman Ghosh from Raman Research Institute and Shaumok Ganguly from my institute, which is Indian Institute of Science. So let me start with basic motivation. We know already that Bery phase or Pancharatnam Bery phase in general, when you remove adiabaticity or cyclicity, is there for spinor in the presence of magnetic field. In the magnetic field, if spinor is moving, phase upwards, Bery phase. On the other hand, magnetic fields have many similarities with gravitational field. For example, both of them create curvature and so on. So we can generally imagine perhaps similar effects could be there when spinor is propagating in curved spacetime as well, because there is a coupling between spin of the particle and the spacetime curvature, particular spin connection for Kerr metric rotating black hole. So basically, they lead to 2 terms, spin field and spin potential coupling. I'll discuss in detail. And so basically, spin orbit type term and the Aronoff-Bohm type term will arise. So to understand, to investigate that in detail, one should start with Dirac equation curved spacetime, that I'll do. And once we write the Dirac equation curved spacetime, rest follows same as there in magnetic field. I may need to go for local coordinate to make sure that it is Lorentz invariance, etc. Only question is if that can be measured. For magnetic field, I can tune the field. It is in my hand. Lab, I can set. But in curved space-time, say Earth, everything is set. Black hole, spin, mass, set. How to measure? Length scale, huge length scale. That I'll try to enlighten as much as possible. Slight recapitulation. Dirac equation in electromagnetism. We know this 4-vector vector potential is there. And energy, we can write mu is 0, giving rise to energy. We can recast this into this form. And this is the spin orbit coupling and give rise to the geometric phase. Magnetic field and spin are coupled. And if I go for non-relativistic limit, energy is consisting of Coulomb term, Coulomb energy, kinetic, and this spin field coupling term. That is prime interest for the present purpose. And Zeeman splitting, just for further recapitulation, positive and negative energy, and further due to spin, further split. Now, what happens for curved spacetime? Generally, it is convenient to use pseudo-Hermitian approach to write the Hamiltonian in curved space, or in other language, condensed matter language, eta representation, because Dirac Hamiltonian in curved spacetime is not guaranteed to be self-adjoint. Locally, it is easy to see some anti-Hermitian term comes. Long debate. Finally, there's a paper, Huang and Parker in 2009. Then they argued that actually you have to consider dot product appropriately to make sure everything falls in place. And yeah, that's a different story. Maybe first day, some of them were looking at this issue. I'm not very sure. Title was telling someone might be talking about this. So how to go to pseudo-Hermitian approach or eta representation? Basically, I define another matrix rho and another matrix eta related like this. And with rho, Hamiltonian is following this relation. And if I consider eta, and then we get H eta Hamiltonian, eta representation Hamiltonian, and that H eta is actually follows, Hermiticity, Hermitian conjugate thing is, intact. So that's the eta representation formalism. And accordingly, wave function is changed in the new coordinate. This is the wave function. And that exactly dot product. So either of the ways, either you can see we'll redefine dot product, you'll introduce rho in the dot product, and you will carry our existing Hamiltonian, or you will go for H eta with new wave function and conventional dot product. Either of them equivalent. So for the present purpose, we'll consider eta representation H eta. So Dirac equation in strong gravitational field, I can write down this covariant derivative has partial term and then spin connection. This is involved in this community, everybody knows, I believe, with metric, more precisely Fierwine and Dirac gamma matrix. That gives this spin connection. If I substitute this and expand, this H is basically I del T. Rest I keep on the right hand side. This is a Hamiltonian. This gamma T, gamma theta, gamma phi, etc. are actually not really flat gamma, but global gamma, Dirac gamma matrices, and similarly spin connections. One easily can obtain all the quantities depending on the metric coefficient. So we consider for the time being Kerr metric in the Boyle-Lindquist coordinate. And so once we know the metric, we know the expressions explicitly, we can compute all the quantities gamma T, gamma R, and so on, in corresponding Fierwine and global Dirac gamma matrices, we can get H eta. In eta representation, Dirac Hamiltonian. Now, importantly notice that two potential now. One is A, another K. A is associated with Lorentz vector, and K is pseudo vector, associated with Lorentz pseudo vector. Interestingly more, K is proportional to the spin of the black hole. If black hole is non-rotating, K vanishes, but A survives, independent of spinning or non-spinning, Schwarzschild or Kerr-metric. So this is more like, I'll show you soon, more of spin orbit, I mean, Bery-like term. This is more of, okay, I'll come later. This is basically pseudo vector multiplied by the potential, and this is again potential in multiplied by Lorentz vector. And if I go to local coordinate, del 0, I can write corresponding Hamiltonian P0, and then I write the Hamiltonian local coordinate. These Roman indices correspond to local coordinate, and T r theta are global coordinate. So we'll concentrate next this. So once we have the Hamiltonian local coordinate, we can use all the local coordinate machineries, Hilbert space machineries. We assume this is the wave function following any standard quantum mechanics, say advanced quantum mechanics, J.J. Shakurai, for example. With further approximation, say weakly rotating black hole space-time and non-relativistic for the present purpose, and quick comparison with magnetic case, we do this approximation, and that Hamiltonian reduces to this simple form, non-relativistic form, kinetic, and then this interaction. Earlier, you remember for magnetic case, sigma dot B. Here, sigma dot IK minus IBG. BG is actually gravitational field, which is with curl of A. Remember, A is this potential, and A is inversely proportional to the radial coordinate. Remember, and curl of A is field. And so, okay, so this is the Hamiltonian we have to concentrate rest. So now so this is the Hamiltonian, this is the interaction, this is the prime interest. Rest, as I said, will follow conventional approach. Like in magnetism, we consider Poincare sphere. Here, without exception, we'll do that because everything falls in place. This is the interaction, total B contains K and A both. And in the Poincare sphere, we write B in terms of Poincare sphere coordinate, like zeta, xi, angle coordinates, and radius vector, magnitude of the radial coordinate B. And there is an interaction Hamiltonian according to Poincare sphere. Once we know the Hamiltonian, we can obtain the eigenvector, and rest is just trivial matter. Bery connection and Bery phase can be easily obtained. In this Poincare sphere, grad that is there, and vectors are there, and we obtain the quantity AB and phi B. So mathematically speaking, this Bery phase looks very similar in Poincare sphere as we have magnetic field. Tilde, xi tilde is basically corresponding to integrated xi. But mathematically they look same. But as I said at the beginning, angle coordinates have different meaning in the sense that they are now determined by they are set by the space-time nature. Black hole spin, black hole mass, if black hole has charge, black hole charge. I don't have any control. Also, you know, if length scale is huge. So for a given arc length where particle traverses, you may have different angle. Or other language, these are radius vector, slight deviation angle. If this is huge, for same angle, you can have big arc length. So determined by the geometry, and it is not in our hand. So big question is how to measure. Magnetic field, laboratory experiment, it is in my hand. How to measure in generally in gravity. So we try to enlighten this thing quickly. So we know in the first place, any quantum effect is measurable if underlying length scale is of the order of or less than underlying particles de Broglie wavelength. L less than equal to h by p. For a black hole, length scale involved is gm by c square. It has to be less than h by p. P is the momentum. If this is the case, then mass has to be less than 15 by p. P is the momentum. For a proton of velocity 1 kilometer per second, quite non-relativistic, mass has to be less than 10 to the power 20 gram. So it has to be primordial type black hole. For M solar mass black hole, momentum has to be 7 to the minus 33 CGS, too tiny. More the mass of the black hole is smaller the momentum. So it is very difficult to measure. So primordial black hole seems to be better bet. And we know, even though there is a Hawking radiation, all primordial black hole of mass 10 to the power 15 gram or high still could survive. So they, in principle, could be there. For an electron moving around Earth, for example, velocity has to be minus 9 centimeter per second, too tiny. So basically, idea is not difficult to understand this. Larger the L, smaller the B or A is, because they are inversely proportional to R, smaller the geometric effect is. So small black hole, which is in any case, quantum effect is more important in small length scale. Smaller the black hole, smaller the effect is. So at least for the present formalism, we assume non-relativistic particle and weakly rotating black hole. Astrophysical black hole seems to not have any significant or measurable effect, but theoretically it is there. So I'll summarize. So Fermion couples to space-time curvature, giving rise to spin-orbit coupling. Basically, two terms arise. One is Aronoff-Bohm type term, another is Berry-Pancharatham type terms. Aronoff-Bohm type terms goes off when black hole spin is 0. But even spherical symmetry, Schwarzschild black hole, Berry-Pancharatham type terms still there. So, but importantly, I forgot to mention, as because I have another 1.5 minutes perhaps. Remember, magnetism based Berry phase tells field has to be varying. Then only phase is there. But here, even if field is constant, gravitational field is constant, but this potential is varying, still I have phase through Aronoff-Bohm type term. But a black hole, sorry. So it is last slide. So non-relativistic proton moving around a primordial black hole of mass 10 to the power 20 gram or less, geometric effects are finite, perhaps measurable, depending on technique you have in your hand. And as I said, this result is only for a special case of non-relativistic particles and weakly rotating black hole. General phase may give more robust result that we are doing generalized covariant gravitational Berry connection and phase. If it is only primordial black hole based result, how to assure? So basically, there are missions, planned mission. So planned missions are that Fermi satellite, for example. Fermi satellite argues that a small interference pattern could be seen in the gamma ray Fermi satellite based, which is determining gamma ray burst. So if that Fermi satellite looks at, able to observe those interference pattern, primordial black holes could have been realized, not any more hypothesis. So I'll end there. Thanks.
Okay, let's thank Manipata for the presentation. We have time for 1 or 2 questions.
Yes, I did not understand something. You are on Kerr spacetime, which is vacuum, and you have an electromagnetic field that inside your Dirac equation. Where does that come from? What is that?
No, I don't have electromagnetic field inside Dirac equation. Let me re-emphasize again the fact.
No, you have an A there. What is the A?
Gravitomagnetic effect.
I'm coming. I'm explaining you again. Initial A is electromagnetism. Just for recapitulation, our actual new result starts from here, and that A is gravitational A. This is related to space-time curvatures, metric. That is gravitational A. Two potential A and K. K is spin dependent, black hole spin dependent. A is black hole spin independent. I mean, it may have black hole spin, but does not determine. It is not determined by. It does not vanish if black hole spin is 0. So if you are talking about this A, which finally comes here in BG, which is curl A, this is gravitational A, nothing to do with electromagnetism. Does that answer the question?
Yes, thank you.
Right.
Sure. Thanks.
So I have maybe one quick question. Sure. Shadi and I, together with Ebru and other people, Eric, also been working on Dirac's equation on space-times which have naked singularities. So I suppose, since you are talking black holes, you are thinking of Kerr space-time with as a black hole space-time. Of course, you are speaking of primordial black holes. So that means you would have to define your Dirac operator presumably outside of the event horizon with some distant coordinates.
Yeah, I am assuming my result is valid only outside. Yes, please carry on.
And so, I mean, there is work by Finster and Yao on that. And if I remember correctly, I think there are no eigenvalues of that operator. And so now you are computing some correction to the eigenvalues that you assume are there. So I think that if one tries to do it really rigorously, I understand you are doing a lot of expansions here, but if you try to do it rigorously, some of the effects may actually not be there. So there are some bizarre things going on in the Dirac equation in general relativity that are very, very different from what we expect based on our special relativistic knowledge. So that's a comment.
Actually, yeah, thanks for the question. First of all, this result can be extrapolated for naked singularity by assuming curve parameter to be more than 1. That is a mathematical extension. But what you are talking about in place of non-relativistic limit, if I go for full Dirac equation, what is the consequence? As long as geometric phase is concerned, that we are doing right now. But earlier we had rather, even I know I am aware of some of the work of Finster. We have series of work which is discussing Dirac equation in full curve space time, corresponding baryogenesis. Those so-called this term, you know, sigma dot b type terms. Those terms were always there. I mean, we'll have it had different different form, not exactly sigma is non-relativistic approximation spin, but more of basically in those cases terms are like gamma 5, gamma mu b, and another is I, gamma mu, a mu. So one is Lorentz vector, Lorentz pseudo vector. So and those kind of terms are actually there. Right. So
just that maybe later by some emails, because we are really unfortunately running out of time. And that
sure. Yeah, I'll send you the paper. Okay. Thank you.
Let's thank Mani Bratna again.
Yeah.
And Shadi is taking over for introducing the next speaker.
Yes, Alexander, please share. Bani Brata, you need to unshare.
I'm sorry,
start the demonstration.
I thought automatically if the next one shares, it will be answered. Let me see. Is it answered now?
Yes.
Okay, yes.
I'll be back.
In this talk, we consider application of Newman-Penrose formalism and the associated debye-potential method, which become widespread in analysis of field equations of different spin in type D matrix. To the case of matrix of type N in Petrov-Pirani classification. In particular, we consider the case of PP waves matrix, which has applications both in astrophysics and in various theoretical aspects such as supergravity and holography. The metric of PP waves were first introduced by Brinkman in 1925. Later, they were interpreted as representing the gravitational waves. Here is the isotropic tetrad by Newman and Penrose, which only one non-zero Ricci rotation coefficient, Weyl scalar, and non-zero component of deviator of Ricci tensor. On this slide, you can see the standard procedure introduced by Hoyts for constructing a solution of free field equations using Debye potentials. First, we add the source in right-hand side of original equation, and then project it onto the Newman-Penrose tetrad for spinor diet using the tau operator. In the resulting system of equations for scalars, the variable can be separated by action of the operator S. Then the solution of our original free field equation can be written as application of adjoint operator on the Debye potential, which satisfies the following equation. In the case of electromagnetic fields, the separation of variables can also be performed for non-vacuum PPV. After projecting the equation onto the Newman-Penrose tetrad, we obtain the system of equations for three Newman-Penrose scalars for scalar quantities. Metrics of type n have only one principal null direction in contrast to the metric of type d. Therefore, a decoupled equation can be obtained only for one scalar quantity, phi 0. The solution of vector potential is constructed using the adjoint operator from current path. Contraction of rich tensor with solution for vector potential give us the zero, and this solution also automatically satisfies the Lorentz-like gauge fixing condition. When considering the equation for spin 1/2, the Weyl equation, it is necessary to turn to the formalism of two component spinors. In this case, we will no longer deal with a tetrad, but with a spinor diet. As a result, the massless Dirac equation for the spinor key and also in components this equation. Further, according to similar scheme for a vector field, one can compose a separated equation for component key 0 and construct the solution in terms of Debye potential, which in turn satisfied the D'Alembert equation. We consider the Rarity-Schwinger field for spin 3/2 only for the case of the vacuum PP waves. After rewriting this equation in spinor formalism, it is necessary to pass from a spinor with mixed dotted and undotted indices to a symmetric spinor with non-dotted indexes using this relation. For equations of spin greater when or equal of 3/2, it is necessary to take into account the Bohdal consistency condition. In our case, it will be satisfied automatically. For equation for a symmetric spinor, we can separate the variables and construct the solution for initial spinor. This spin 2 field on curved background is described by Lichner-Rolitz equation. To separate the variables, one should use the Bianchi system of identities for Riemann tensor in Newman-Penrose formalism. In this case, the variables included in this system, including tetrads, spin coefficients, Weyl scalars, differential operators, and deviators of Ricci tensor, should be decomposed into the background zero part and the part of perturbations with subscript 1. After a series of manipulation and use of Ricci identities in Newman-Penrose formalism, we obtain the separated equation for psi0 perturbated, and then write down the solution in terms of the bipotential, which will satisfy the original equation and the gauge fixing condition. As in the case with vector field, the solution will also be valid for non-vacuum PPV. In this slide shows the complete family of solutions for fields of different spins in terms of the bipotential. It can be noted that equation for the bipotential is universal. In this table, you can see the variables, the scalar variables for electromagnetic fields, the symmetric spinor for the Rayleigh-Schwinger field, and the perturbated part of Weyl scalars for the gravitational perturbation. Great attention is paid to such a subclass of PPVs as the matrix of black holes in infinite momentum frame, i.e. of black holes which are formally but boosted up to the speed of light. This matrix represents gravitational shock waves and have delta-like singularity at the point u equal 0. The function fx is a function of a gravitational wave profile. This slide shows several functions corresponding to the boosted Schwarzschild metric. This is the metric Eichel-Booth-Saxon metric, boosted Einstein-Maxwell-Dilaton solution, OED diametrics, boosted Tau-Bnut solution, Newman boosted Newman-Whitney Tamburino metric, also known in literature boosted Kern-Newman solution, boosted Schwarzschild anti-de Sitter, and others. The equation for the bipotentials on the background shock wave matrix contains singularity. This is the singularity of this equation. For the first time, we construct the exact continuous solution in terms of generalized function, and as well as the solution to the Klein-Gordon equation. Weyl's equations are the special case of massive direct equation for B-spinor. Its solutions for the case of shock wave background is a summation of previously obtained solutions for massive field, and can be written in the following form. This solution is a modified solution in the bipotentials, and we include mass to this solution. The Proca equation describes massive spin 1 field Let us note here that the gauge invariance of Maxwell field is broken for the proper theory due to the mass term. Instead of a gauge fixing condition, we have deal with Lorentz-like dynamical constraint. Unlike a massless one, where massive vector field has not 2 but 3 degrees of freedom. The first two polarizations are realized by means of modified solutions for the Debye potential. This is a real and imaginary part of that solution. The third polarization can be obtained for the action of covariant derivative of the Debye potential itself. And this is the third polarization. Wave equations for fields in curved space have been extensively studied since early 1970s. The Newman-Penrose formalism and the method of constructing solutions using Debye potentials were successfully used to construct solutions for equations for massless fields with spin on the background of vacuum black hole solutions of general relativity of Petrov type D, since they made it possible to effectively reduce the number of real functions, connecting free field massless field of higher spin to 2 by means of one complex function, the bipotential, which corresponds to their number of degrees of freedom. As it turned out, this formalism is applicable to wider class of metrics, in particular to metrics of pp-based belonging to type M. Construction of solutions describing the propagation of fields against the background of play-wave metrics is a demand in the context of various theories, including problems of radiations in the process of transplanting scattering of test fields. We have also found their way into supergravity theory, superstring, and holographic models. Thank you for your attention.
Thank you very much. Let's thank the speaker. Any questions or comments?
Maybe a quick question, since we do have a little time, even though we don't have much time left for the whole section. But okay, so you're using separation of variables for the Petrov N-type. Do you think that this exhausts all separation of variable situations now, or do you suspect one will still be able to make progress in some other type of metrics of the Petrov class, for instance?
The formalism, the Newman-Penrose formalism, widely used for separation of variables to type D metrics. We use this formalism to separation of variables in type N metrics for our types of metrics. This procedure not used yet, and this procedure is specified for and adopted for the type D for the first time, but For PP waves, we have no problems with separation of variables with Newman-Penrose formalism.
Okay, thank you.
All right, let's thank the speaker again. So this concludes our regular part of the presentations, and now we move on to the contributed paper section, which are 5-minute talks. Michael.
Okay, so fortunately, these are very short talks. So please, everybody, you basically have time to say what the problem is and what your result is. You don't have time to explain any details in 5 minutes. So the next speaker will be Mikhail Klopunov, sorry. And could you share your screen, please?
Oh,
first, Alexander, you have to stop sharing, please. Okay. Okay. So Mikhail Klopunov will speak about retarded potentials and radiation in odd dimensions, please.
Yeah, thank you. Sorry. Free massless fields of any spin, if when in flat arbitrary dimensional spacetime, propagate at the speed of light. However, kinematics of the retarded fields in odd dimensional spacetime significantly differs from that in even dimensional cases due to the violation of the Huygens principle in odd dimensions. The most transparent way to illustrate it is to consider the corresponding Green's function. Retarded Green's function of the D'Alembert equation in d dimensions is defined by the present equation and provides us with the corresponding solution of the D'Alembert equation. Solutions to this equation are given by two recurrent relations separately for even and odd dimensions. While in the even dimensional retarded Green's functions are given by the combination of delta function and its derivatives localized on the light cone, the odd dimensional ones are given by combinations of Heaviside function and its derivatives, leading to the localization of the odd dimensional Green's functions not only on the light cone but also inside it. Therefore, the odd dimensional retarded massless fields propagate in space with all velocities up to that of light, depend on the entire history of the source motion preceding the retarded moment of time, and diverge on the light cone. Oh, I'm sorry. And diverge on the light cone. Due to these properties, extraction of the emitted parts of the fields in a standard manner becomes non-trivial in odd dimensions and requires a more sophisticated approach. Such an approach was suggested by Rohrlich and Teitelbaum and is based on the use of certain covariantly defined quantities. Let us consider the point particle moving along arbitrary world line and assume the observation point to be the top of the light cone in the past. The moment of particle's proper time corresponding to the intersection point of this light cone with the world line is called the retarded moment of proper time and is given by the present equation. Further, all the headed quantities are assumed to be calculated at this moment. Let us introduce the following d vectors. The first one is the light-like vector x capital directed from the retarded point of world line to the observation point. The second one is the unit space-like vector u orthogonal to the particle's velocity. And the third one is the light-like vector c given by the sum of the particle's velocity and vector u and aligned with vector x capital. Properties of these vectors are presented on the slide. Also, let us introduce the Warren's invariant scalar rho hat, which is equal to the spatial distance in the Lorentz frame moving with the particle at the retarded moment. When the observation point is far from the particle's world line, it's equivalent to the spatial distance between the particle and the observation point. In what follows, it is the Lorentz invariant parameter rho, which is used in the Rohrlich-Teitelbaum approach for the expansion of tensors and definition of the wave zone. According to the Röhrlich-Teitelbaum approach, the emitted part of the retarded field is defined by the expansion of the field's on-shell energy momentum tensor. In d dimensions, the on-shell energy momentum tensor can be expanded in the inverse powers of ρ as follows. The first term is the energy momentum tensor of the deformed Coulomb part of the field. The second one is the mixed part, which consists of more than one term in dimensions higher than 4 and is absent in 3 dimensions. The last one is the long-range part of the on-shell energy momentum tensor, which admits properties allowing us to associate it with the radiation energy momentum tensor. The first one is that it is separately conserved from the other parts of the energy momentum tensor. It is proportional to the direct product of 2 light-like vectors, corresponding to the propagation of this component in space exactly with the speed of light, and it gives positive definite energy momentum flux through the distant sphere. As a result, the flux of radiation energy through the distant sphere is given by the present formula. While the radiation power is calculated in a standard manner, in odd dimensions, it depends on the entire history of the source motion preceding the retarded moment of proper time. While initially the Röhrlich-Teitelbaum approach is based on the splitting of the on-shell energy momentum tensor, usually its structure is just the bilinear form of the field's derivatives, which provides us with the possibility to extract the emitted part of the retarded field's derivative. To begin with, let us consider the case of the massless 5-dimensional scalar field interacting with a massive relativistic point charge moving along a fixed world line. The action of such a system has the following.
Last minute, so please try to come to the punchline.
Punchline, okay, I will try.
No,
it's possible to show that introducing regularizing parameters into the retarded green functions, into the delta and Heaviside functions, we can first of all demonstrate that the resulting sum of 2 divergent terms is finite. The most transparent way to do it is to consider the field of the static charge, and considering the arbitrarily moving relativistic point charge, we can show that the long-range part of its derivative have the following form, where only the first term in the integral contains all the physical information about the properties of field in the wave zone, while the last 2 terms just subtract the divergence from the first one contained in the upper integration limit at the retarded moment of proper time.
We have to go on. Sorry, Mikhail. So what's the last slide? Show the last slide just to someone.
Just the last slide. As I said, in odd dimensions, green function retarded localized on the light cone. Retarded fields propagate with all velocities up to that of light. Retarded fields also diverge on the light cone, but using the Röhrlich-Teitelbaum approach, we consider the wave equations for spins 0, 1, and 2 in 5 dimensions, and in all these cases, we found that the resulting retarded fields are finite, despite the present divergences in them. The long-range parts of the retarded fields propagate exactly with the speed of light and depend on the entire history of the source's motion. And the long-range parts of the energy momentum tensors propagate also in space exactly with the speed of light and gives a positive definite energy flux through the distant sphere. And we can associate them with the radiation energy momentum.
Okay. I think thanks a lot, Mikhail, for the conclusion. Thanks for the talk. And Shadi will introduce the next speaker. Any questions, please direct them to the chat.
Marcello, please share.
Okay, let's see.
Yes, the next speaker is Marcelo Rebucas, and you will see his title. Go ahead, please.
Yes. Can you hear me?
Yes.
You see the screen, is that fine?
Yes, yes, go ahead.
Okay, well, I'll just tell you what we've done. In the reference are here, down here, In the first paper, we make the following problem. We had under vacuum fluctuation of the electromagnetic field, point particles, and study how would be the movement of this point particles with in Minkov space-time with different space topologies. Actually, we show that if the space-time is simply connected, we have no movement. But as long as we took one multiply connected spatial second, the particle moved in a random movement. The paper that I am trying, I will tell you a bit more than the first one that was published in class in quantum gravity I have just mentioned, is the next one that is being accepted. And we asked, after the first paper, we asked whether we could extract topological properties of the space-time using the same scheme, inquiring the electromagnetic quantum fluctuation about the orientability in the first paper of the space. And this is the paper that we done that I go to report a bit. Just to remind you, orientability, that is a crab, when he goes along the map strips and come back to the same position, the left and right is flipped. This is an indication of non-orientability in 2D. Of course, we've got orientability in manifolds with 3 and whatever number of dimension. We in this paper, we instead of dealing with freedom of Hauswalker, we just freezed the time degree of freedom and took Minkov space just to focus on the topological properties. So we assume that the 4D manifold has this form, and usually people take Minkov space as a topological space E3. And this is but it is well known since by Wolf book, Space of Constant Curvature, that the 3 space of Minkov's space, actually Euclidean 3 space can be endowed with manifolds topology, if you want, that's quotient topology that's given by this. And actually, is the mathematician, as a matter of fact, Wolf has made the whole classification. Now we know that the M3 spatial topology, we know all of them, it is classified. And then Minkov space, usually people take that, but M3 can have, in principle, can be endowed with any topology of those Wolf.
Marcello, sorry to interrupt. You have 1 minute.
Okay, 1 minute, okay.
Yes.
So here is the list of the classification of possibility in 3-dimensional. We focus on 2, the last 2, one with its orientable and its counterpart that's non-orientable. We study a move of a particle in both them, and we realize at the end that we introduce one indication that measures the departure of the mean root square velocity in the simply connected, and when any multiply connects manifold, this is our indication. And we have shown that it is possible using quantum vacuum fluctuation and particle-like particle to distinguish orientable from non-orientable. We can have an answer, local answer for the orientability problem using quantum vacuum fluctuation and using random motion of particles like charged particle and electric dipole. Here's the final slides. Here we have two manifolds, one E16, which is orientable, and 17 is its counterpart, which is non-orientable. If you see that when it is non-orientable, our indication shows there is a pattern of inversion. So non-orientability reflects in the motion of point-like particle as far as captures, but our indication are a pattern inversion in the movement of particles. That's it.
Thank you very much. So please unshare.
Okay, I will do.
I'm
sorry for that.
Already introducing the next speaker, Dr. Finian Gray, and we will learn something about shock waves as soon as the slides can be put up.
Yes, I just am having problem how I can do this. Yeah, I see. Okay, I did it now. Is that okay?
Yes, thank you. Thank you.
And you can see my screen now?
Yes.
Just introduce your title yourself and keep in mind 5 minutes.
Thank you. So thanks for staying around. I hope you guys aren't getting too hungry. This talk is about quantum imprints from gravitational shock waves, and it came about from the PSI winter school that was run by Perimeter Institute, and it's in collaboration with all these people, including a couple of master's students and my supervisor, David Kubznak. So the main motivation for this work is that gravitational shock waves are a way to physically implement a super translation, and super translations have come up a lot recently in terms of soft hairs on black holes, and maybe there's extra information associated with these soft hairs. Unfortunately, recently, most work is either focusing on classical effects like the gravitational memory effect, or in not readily observable, at least to local observers, physical things like Bogoliubov coefficients and soft factors in the S matrix. So we took the point of view that information is physical if you can extract it with an auxiliary system. And so we want to kind of have an operationally sensible way of defining this kind of thing using the entanglement harvesting protocol. So hopefully I get through all of that. So briefly, thanks to Alexander, I don't have to focus too much on gravitational shock waves. We've already seen them before. Essentially, they are an exact plane wave solution of the Einstein equations, which has an energy density localized along a particular null coordinate. And that energy density is basically related by solving the Einstein equations. The nice thing about these shock waves is that they are exactly flat either side of the shock wave, and you can think of it as being like two halves of Minkowski stitched together with a shift along it, and that's where the gravitational memory effect comes in. Because you have these flat spacetimes either side of the shock wave, there's two equivalent ways of quantizing a scalar field on this background, and one you start in the asymptotic past and demand that it's a plane wave solution, and the other you start in the asymptotic future. Now, this gives you two physically maybe different vacua that you can use for your quantum field theory, but actually turns out if you consider observables like the number operator, there's naively no particle production, which says that these two vacua are at least Poincare equivalent. As it turns out, if you introduce local observers, this is not necessarily the case. So what do I mean by local observers? Well, I'm talking about, let's say, Alice and Bob, who carry some particle detectors. And these particle detectors are captured by the Unruh-DeWitt model, which basically is a simplified version of the light-matter interaction where Alice carries a two-level quantum system that couples to the scalar field pulled back along her trajectory. So that would be like an atom that has a ground state and an excited state, and when a photon comes in, it goes to the excited state. Now, we can set these two people up in such a way that they are exactly in flat spacetime, and naively you then expect them to just be able to see flat spacetime and not the shock wave. However, if you prepare them in a state that's initially uncorrelated, so Alice has her density matrix, Bob, and then the field, and then you evolve them with this Hamiltonian, and you trace out the degrees of freedom of the field, so you're just left with Alice and Bob's degrees of freedom, you end up with extra correlations. And the question is, how different are these to just ordinary flat spacetime? And so the key point is that you can measure correlations between Alice and Bob using your favorite measure of entanglements. In this case, we're using concurrence. And you see that the blue line is the concurrence of Alice and Bob, and that greatly increases where we place Alice at some position and Bob at another position and move Alice closer to Bob for a shock wave that's centered around the 0 here. And in fact, there's even a point where you get detection of this shock wave through increased entanglement when Alice herself doesn't cross over the shock wave. So this provides a physical construction where you can get actually extra entanglement, and you can have a quantum imprint of this shock wave, which has relation to, like I mentioned at the start, things like soft hairs on black hole. And so maybe gives you a way of actually quantifying this information. Anyway, that was extremely quick, but thank you for your time and thanks for the opportunity.
Thank you very much and for staying in time. And the last speaker will be introduced by Shadi, and I believe that we should be able to go 3 or 4 minutes over time now to be giving everybody the
Okay, the last speaker for today's session is Alexander Yefremov. Talk about hypercomplex medium. Please go ahead.
Thank you. We draw attention to hypercomplex numbers as to a specific medium immanently containing physical laws once discovered empirically or heuristically. We make accent on quaternions or Q numbers. Next. Discovered by Hamilton, Q numbers are built on one real scalar unit and 3 non-commuting imaginary vector units. Q vector units, imaginary units, behave like a Cartesian frame. The scalar unit until recently had no clear geometric image. We will give it in a minute. Q algebra is stable under Q units, orthogonal rotations, or related spinor mappings. The Q medium hides many physical laws. First, Rudolf Furter analyzed Q functions of Q variable and postulated for them a Cauchy-Riemann type condition. The pure math expression has exactly the form of vacuum equations of electrodynamics. Now, a simple definition of a Q vector derivative gives the full set of Maxwell equations with source. Second, SO3C group, which leaves Q algebra invariant, is one-to-one isomorphic to the Lorentz group. This generates a specific rotational relativity theory with the Q vector line element being a square root from the standard space-time interval. This theory gives all effects of Einstein's special relativity, but not suitable and fruitful. It is for solving problems with non-inertial frames. Third, next slide. Third. Only once speaking of foundations of quantum physics, John Archibald Wheeler mentioned some pre-geometry. Q medium really gives a variant of pre-geometry. Using a spectral theorem, one finds that all Q units are composed of simpler elements, 2 dyad vectors, that determine an area on a surface, 2D cell. So the 3D geometry may be said generated by an invisible subspace or pre-geometry. Compared to a 3D space, the 2D cell is fractal, its dimensionality is 1/2. We immediately find the metric of the 2D cell is nothing but the scalar unit. Moreover, any complex number acquires a fractal image of a Koenig-Gehring couple, its shaft forming the 2D cell. Primitive distortion of a 2D cell oscillations and stretching ruins the algebra units. To cure the algebra, we introduce natural saving and stability conditions over an abstract space. This gives a pure math continuity type equation containing a free vector. Simplest choice of this vector as an oscillation phase gradient makes this abstract equation fractalize and take a simpler form. Written in the physical microworld units, this fractal stability condition becomes the Schrödinger equation of quantum mechanics. For a more complicated form of the free vector, the stability condition becomes precisely the Pauli equation. This approach leads to non-standard quantum mechanical solutions. An example is a solution for a stationary non-static model of hydrogen atom. In this model, the angular momentum is automatically quantized as in Bohr postulate. The electron's density is distributed along the orbit. Fourth, using the so-called Bohm procedure, we reduce the mass stability condition to Hamilton-Jacobi equation of classical mechanics and to Newton's dynamics. Moreover, double fractal and 3D models of the same particle entail the action functional for special relativity normally postulated and an original helix-type Minkowski diagram. So all branches of mechanics, quantum, classical, and relativistics are deduced from pure Q math. The details of this general theory of mechanics are in the book issued by a British company 2 years ago. Well, we see that the specific mathematical equations born in quaternion medium in proper physical units become non-physical laws. These coincidences are hardly incidental, and they motivate to move ahead in this direction. In future, we look for a structure of electric charge and for a Q-rotational gravity naturally split into spinor structures, which can reconcile relativistic gravity with quantum physics. Thank you very much.
Thank you very much. This concludes our special session. Thank you everyone for attending. Thank you all the speakers, and we wish you great success in all your endeavors.
Same from me also. Thanks everyone for being here today and giving the presentations, and best of luck. And any further questions, either by email, I think the emails should be all available on the websites. And yeah, I think that's the best we can do. We're a little bit over time. They will cut us off sharply in a few minutes. Okay, everybody.
Thank you very much.
Thank you to you both for organizing as well.
Thank you.
You're welcome.